Today's lesson, Piecewise Functions. And I think math titles like this are funny when the title of the lesson is something that doesn't get explained till later in the lesson. So if I say piecewise and you're like, I have no idea what you're talking about, yeah, that's right. Hopefully by the end, you'll be like, okay, now I see what a piecewise function is. Introduction. This is how we show what a piecewise function is. Because as you go to do the homework, there might be these moments like, where does this even come from? How would anyone even come up with this? And this is supposed to be like a motivating example to say, this is how this could happen, why you'd have a piecewise function. A city parking lot uses the following rules to calculate parking fees. They charge a flat fee of $5 for any amount of time up to and including the first hour. So if you go there and you park for 5 minutes or 10 minutes or 20 minutes or 30 minutes or for a full hour, you pay $5 for that first hour. If you use more than an hour, they charge a flat fee of $12.50 for any time over 1 hour and including 2 hours. After that, it starts at $13 and goes up by $3 an hour. Actually, some parking lots use something similar to this. The reason they do stuff like this is they want somebody who just uses the parking lot really quick, come into a store at the mall or whatever like that, and then leave. They don't want them to have to pay too much. If you're going to stay longer than that, you got to pay a lot more. However, if you're somebody who maybe works at the mall, they don't want it to go too crazy, so they charge you $3 an hour. And we're not used to this in Brantford, actually, because Brantford's pretty much, only if you go downtown Brantford, you put maybe a quarter in or a loonie in to park. We're used to free parking everywhere. But big cities, it's just not like that. Anywhere you go to park, you're going to pay for parking. Maybe the hospital, if you've ever been to the hospital, you pay there. And they've got a system that's not unlike this for their employees versus patients, all that kind of stuff. What do you think a graph of cost versus time would look like for this situation? Well, it's a big mess is what it is. There's these different rules for different sections of the graph, and you got to really think it through to try and figure out what a graph would look like, because there's not one rule all the way through. As complicated as the functions are that we've done so far, at least it was the same rule all the way through. Once you figured out what was going on, you could just draw the whole graph. This one's not like that. It's got different rules for different sections of the graph. So let's take a look. Flat rate of $5. Now, just to think that through, that means in the first hour, if you spend 5 minutes there, you pay $5. You spend 10 minutes, you pay $5. You spend half an hour, you pay $5. It's always $5. If you want, it's a line with zero slope. It's not going up at all. So what you get in the first part of the graph is this right here. And I'll deal with the open dots and the closed dots at the end. I'll loop back that at the end. But you can see in this part right here, and let me try and get a pointer here, laser pointer. Right in here, that section right there, it's always $5. You say, well, what happens if I'm there for 20 minutes? $5. What happens if I'm there for 40 minutes? $5. What happens if I'm there for a full hour? $5. Now, if you go over that first hour at all, even by 1 minute, if you get into that second hour, you immediately jump to $12.50. So instead of paying $5, you pay $12.50. And you see the jump there? Now in that second hour, any amount of time in that second hour, an hour and a half, you're paying $12.50. Hour and 3/4, you're paying $12.50. So whatever time you look at there, you're paying $12.50. Okay? Making sense now a little bit? Not too complicated, but the rule has changed at different spots. And I'll come back to the open and the closed dot to make sure those make sense. Next, if you stay after 2 hours, and this would be like somebody who works there, we don't want to totally kill them on parking, although they do. They really do. People who work at a place pay a lot for parking. It's a big deal in Toronto to get a job where it's free parking. It's like a special perk. Yeah. Anyways, a flat rate of $13 plus $3 an hour for everything over $2. So you see, at 2 hours, you start at $13, and then it starts going up by $2 every hour. So after 3 hours, it's up to 15 right there. After 4 hours, up to 17, and it just goes up by $2 an hour. Or sorry, by $3 an hour from there. 13, and then after 3 hours, it's up to 16. After 4 hours, it's up to 19. Actually, this is leaning towards how I'm going to encourage you to graph them. It's just to do a table of values for each section, and then you'll have the graph. It takes a couple minutes, but it's really not particularly difficult. You don't have to memorize every particular part of the graph. You just get your table of values going, and you'll be done in just a few seconds. Yeah? And I'll show you that afterwards. What about the open and closed dot stuff? Well, I like the closed dot here at 0, 0. If you go to the parking lot for 0 hours, you pay $0. That makes perfect sense. If I don't go, I don't pay. But maybe there's a little bit more to it than that. I've done this before where I've gone to a parking lot, pulled in, and then gone, oh, wait, this isn't the right parking lot. Or, oh, you're charging for parking? And just looped back out. They didn't charge me for that, yeah? Here, closed dot at the 1 hour mark at $5. If you're exactly an hour, you stay there. But open dot here at 1 hour, it doesn't exist there. You don't pay the $12.50 at 1 hour. So they put an open dot going, no, not here, down here, yes? And same here, closed dot at $12.50. If you're exactly 2 hours, you pay $12.50. Then open dot at 13. You don't go there unless you get past that 2 hours. Any questions on that? Not too hard to comprehend that part of it. Yeah. The next part is a little bit weird. Notes. The domain happens to be x element of reals, such that x is greater than or equal to 0. It doesn't look like it when you first look at it. It looks like there's moments where that wouldn't be in the domain, but they're all in the domain. You can go any number of hours you want, but it's gone greater than or equal to 0 because you can't go park for negative time. You got to park for 0. We could even argue. Some people would say, well, really x greater than 0. Shouldn't it be x greater than 0? Like you're not going to, parking for 0 time doesn't make any sense at all. And I wouldn't disagree with that if you put that on a test. If somebody put greater than instead of greater than or equal to, I go, yeah, I get it. I get what you're saying. 0 doesn't really fit in this. You don't go parking for 0 hours. Okay, so and that's no big deal. What was the next thing? The function is linear over its domain. Most people wouldn't describe this as linear. If I said, oh, this is linear, they go, no, wait. In grade 9, we found out linear was go up by the same amount the whole time. And I'm like, yeah, I agree with that too. Yeah, I like that. Basically, mathematicians will call this linear. They'll say, any section you look at is linear. We're going to call that linear. You might go, I don't like that. I don't like that as linear. I'm not really setting up a test question here. I'm just bringing it up and saying, listen, mathematicians will call this thing linear because it's straight line wherever you look. Okay? The function is discontinuous. It has jumps at 0 right there. It has jumps at 1 and jumps at 2. So there is some discontinuities here. And that's a true jump. Yesterday I used the word jump when those asymptotes came up, and it's the wrong word, but I used it because it sort of helped there. Jump is really when a function starts at some point and then just jumps to another spot. Yeah? And now you can see why that might happen. You might immediately jump to a new price. Notice the use of solid and open dots. Oh yes, I explained that. So what is a piecewise function? Oh, here's the definition right here. A piecewise function is a function that is defined by using different rules on different intervals. I guess that gets the highlighter action here. I'm trying to encourage you to use your highlighters for these things. And that only really helps you if you go back maybe before the test at some point, or maybe when your brain's burnt out. Maybe sometime this afternoon your brain just totally goes, I can't do another question. You take 15 minutes, you flip through your notes, you look for those highlighted things, take note of them and go, oh, yeah, I remember that. Or wait, what was he talking about here? Why is this highlighted? And it's just a different kind of studying to mix things up a little bit. Here's a new example that we might run into. We might run into an example where it says, graph f at x equals x squared for x less than or equal to 0. There's a function we know, x squared. And then it says graph x plus 2 for x greater than 0. And then you get two different graphs of it. Well, let's not wait around to figure out how to do these things. Let's actually do that example. I'll switch over to some graph paper. And I'll graph this function, which is, they said was f at x equals x squared for x, I forget already, less than or equal to 0. And then it's equal to x plus 2 for x greater than 0. And I'm going to approach this like you find this difficult. Because it could be you just look at that, and maybe you're so good at functions you're like already like, oh, x squared for x less than or equal to 0, whoop, done. I know how to graph that. X plus 2, I know how to graph that. Whoop, boom, done. You might be that good. but maybe some of the functions that you're going to see in the homework or on the test, you won't be that good. So check out the procedure I'm going to use on this thing to be able to handle this whole situation. Table of values. I've been preaching that all chapter, right? When lost, when confused, break out the table of values and see if that can help. Actually, the last 2 days I said, just use the table of values. It'll be fine. Sometimes it won't. By the time, when we get to Unit 5, a table of values might not be enough help. And I'm going to have to show you some other stuff. But for now, table of values will bail you out. This week, a table of values will always bail you out. So, 2 different rules. And I'm going to use 2 different colors here. I'm going to say, okay, one rule for when the x values are less than or equal to 0. So I'm going to use like -3, -2, -1, and 0. Then I'm going to switch over and actually draw a line on my table. Maybe you don't need a separate color. Maybe you just draw a line going, okay, there's one rule. There's one part of the function. The other part of the function is when x is greater than 0, and that's going to be 1, 2, 3, 4. Let me just slow this down so that if you're really wondering about how to handle these situations, you can see exactly what I'm going to do. In this section, for the x values less than or equal to 0, I'm using y equals x squared in there. That's the rule in that part. And you're like, well, why would you ever build a function that was x squared for one section, x plus 2 for another section? Well, you saw with the city parking lot, things can change. Oh, you biology people, as soon as conditions change in our biological systems, this is exactly what happens. Maybe there's an oil spill, and all of a sudden, bang, the rules change, and then your population that was doing this suddenly does this. Coronavirus, perfect example. Coronavirus is doing this, right? We get this vaccine in there, you can bet the rules are going to change, and this thing's going to go piecewise on us, and it's going to change rules. Yeah, so it's very applicable. Why aren't we using those crazy functions? Well, the homework does use a few of those, but for now we'll practice on the functions we know, and when you go off to biology, you can work on those functions when you get there. Okay, back to you. Let's see, I got to square each of these because I'm in the y equals x squared part, so I get 9, 4, 1, 0. I'm going to graph those really quick so you can really visualize what we're talking about when we say piecewise. -3, 9. -2, 4, -1, 1, 0, 0. And I've made that dot really thick, and I've closed it, and hopefully you're thinking about why I've closed it, and I'll get back in a second and I'll say, why did I close that dot? Yeah, there's a way to know why I closed that dot. And I'm just going to draw that on there, and then I want to pause and hesitate, because this really gets to the heart of what piecewise is all about. Whatever this situation is, it's y equals x squared when the x values are less than or equal to 0. Why the closed dot? I tried to give it away. It's too early. You don't know, or it's too early? I'll do the other side. I'll give you time to think about it. See if it comes through. Then I go to the other side. And maybe you're so good at graphing x plus 2, you don't need the table of values, and that's great. But maybe in the homework or something, you're going to run into a question that's a little bit too difficult, 2 more difficult functions than this, and then the table of values is really, really helpful. So now I'm going to sub in x equals 1. Let's see. 1 plus 2 is 3. 2 plus 2 is 4. 3 plus 2 is 5. 4 plus 2 is 6. I'm going to graph those points. 1, 3. 2, 4. 3, 5. In the middle of this, when it's lines, it could be that as you're building the table of values, you're like, oh, I was supposed to know that one. That's a straight line. Yeah, I guess I didn't need a table. But it doesn't take long to do a table of values in this chapter, so it's no big deal. So straight line on that part. And I just continue it out like that. Can you really see what we mean by piecewise now? There's 2 different pieces, maybe more than that. Some questions might have 3 different pieces or 4 different pieces, but 2 different pieces to the function. I'm not quite done yet. To really finish these off and get them right, this breaking number here, this 0, where the rule changed, you should put that in the new function as well. And you're like, but you said not to use it. I'm like, I know. I'll get to it in a second. And when I put 0 in there, I get a 2, and that's my open circle, where I go, the point that this thing starts at, but isn't actually there, is 0, 2. So put that 0 into the other function as well to see where your open circle is. I promise to come back to that, and I hope I've now completely explained the open and the closed circle. But do you have any questions about the open and the closed circle I've used there? Do you see why the closed circles with the x squared and the open circles with the line? That's all there is to it. It's piecewise functions, really. If you know how to graph functions, if you can do transformations on them, you're home free. And when stuck, you've got table values to go, oh boy, here we go with the piecewise, and then you can just build a little table values. It helps to know what you're going to get. Like when you go to draw y equals x squared, you're like, well, I'll get the points. I know what the shape's going to be. I know it's going to be a parabola, but I'll just plug it in to get the points that I need. And then you look at this and you go, oh, I know it's going to be a line, so I'll just plug them in to get the exact points, but I know we're talking about a line. It really helps to know the shapes at least. Questions there? More time? I only get to teach once today, so I'm trying to over-explain everything. What is a piecewise function? So I graphed that example. So the graph of a piecewise function contains several pieces, and this is going back to the parking example. They show the parking example here. And we can have, this one had 1, 2, 3, 4 pieces. You can have many, many pieces. The example I did on the graph was only 2 pieces. Can we use function notation to represent the parking situation from earlier? So back to the parking situation, and can we come up with equations for this? The answer is totally yes. Each section has a different difficulty level. So here is the piecewise function for this thing. Let's go through it one piece at a time. The first part of the function, we can argue whether this should be here or not. I wouldn't get excited if you didn't include it. Is that if the x value is 0, the function value is 0. If you want, the function value is how much you're going to pay. If you park for 0 hours, go back to my laser pointer here. Where's my laser pointer? There it is. If you park 0 hours there, you pay 0. You're like, well, duh, right? So, yeah. Now, next, if you park between 0 and 1 hours, how much do you pay? You pay $5 every single time. This actually is the equation of a line with slope 0. Back in grade 9, you called it y equals 5, horizontal line. If you use between 1 and 2 hours, you pay $12.50 constantly. You say, well, what if it's 1.5 hours? You still pay $12.50. What if it's 1 3/4 hours? You still pay $12.50. It's always $12.50. This one's the tough part. This line here apparently has equation 3x plus 7. Well, 2 different parts. Well, the $3 an hour, I understand completely. $3 per hour. But where does the 7 come from? This is weird. 2 different ways to get that number. One would be to get out a ruler. This is what most people would do, I think. And they would get their pen out and a ruler. And they just draw this line back to find out where the y-intercept was at 7 there. So the equation of that line is 3x plus 7. The only other way to do it is to go, well, okay, I do know that this equation has, this part of the equation is y equals 3x, and it has some y-intercept. But I do know that for 2 hours, I should charge $13. So I sub that in. I go 13 equals. And then in a couple of moments, you can solve for the y-intercept of what that line would be. I know the line starts out here, and that's weird. But if it's going to be a y equals mx plus b equation, it has to be a true equation all the way through here, even though I'm only drawing it for this part. Very, very strange. You can get away with right now just drawing that line back and going, what's the y-intercept? You don't have to necessarily go through this. We'll get into more of those subbing type situations as we go along. But does that help to understand the 4 different pieces of the parking lot example? Fair warning. This section of homework, I forget the exact numbers, but it goes 1 to 9, 11, 14. For about 5 or 6 questions, you're going to be like, I love Piecewise. This is so nice. Da, 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 da. And then all of a sudden, boom, the hammer falls. There's an income tax question, there's a cell phone question, and it gets really hard, and you got to check it out, and you got to ask me about it, and you got to make sure you get to the bottom of that. I hope that's a good enough hint for TestWise. And somebody goes, Mr. Todd, is there going to be one like this tax question on the test? I'm like, yes. You can just write that down. There's two types. There's cell phone, income tax. Those are the two ones I always choose from. So check those out. Don't panic about them until they appear. Okay? But sometime today or tomorrow, you got to get that figured out. More questions here? What slide am I on? Oh, just some examples. Sketch the graph of the following piecewise functions. I'm not going through every step here. If you need to build the table of values, you can. I just wanted to show you some other ways that you could do this. So this one's y equals x squared, which is the parabola. And if you're really good at graphing parabolas, you might just graph that parabola, or you might plug them in and make a quick table of values. But this time it's for x less than 2, and that's why we get the open circle right there. Pointer options, laser pointer. That's why we get an open circle right there, is because it's for x less than 2. Now then, 2x plus 3, if you want to just graph that line, what you would do is you would graph 2x plus 3, the whole line, like this. And I'm going to use a color. I'm going to try and choose a color that you can barely see. I think that light blue you worked good yesterday. Yeah? So you draw the line 2x plus 3, but you erase this part. Like, oh, I don't like that erasing thing, Mr. Todd. That's no good. Yeah, build the table of values, like the example I just did. Yeah, you can just build the table of values if you needed to. So that's the line 2x plus 3, and that's the graph of 2x squared. Or sorry, of just x squared. Note that this function happens to be discontinuous. If you graph them both, you can see if they're discontinuous or not. Okay. The only other question they could ask is, determine the algebraic representation. They give you the graph. See, they might give you the equations, and you've got to find the graph. Or they might give you the graph, and you've got to find the equation. And now it's a big test of whether you know your basic functions or not. You got to sort of know your functions at this point. There's no real way around this. No table of values to bail you out. You just got to be able to look at that and go, oh, I know what that thing is. Do you know? What is that thing? Quiz yourself right now. Do you know what that thing is? If you don't, it's like, okay, must study the functions so that I can look at a function and go, oh, I know which one that is. There's only 6 you got to worry about. What is this thing? That's 1 over x. So this thing is the graph of 1 over x up to x value 2. After that, it switches over to this line, which has 0 slope and y-intercept. It would have a y-intercept of 2. So that's the line y equals 2. And there it is. 1 over x for x less than or equal to 2, and then 2 for x greater than 2. So that's a recognizing your functions type question. Your questions? I think this wraps up with one more example. A 3-part one, which I will do with you and go through it one more time. Like, okay, can we do this whole piecewise thing? And I'll talk about that drawing and erasing move, you know, that I mentioned there. New page here. And maybe you want to get out a piece of graph paper to get this down. This thing right here. Front page. There we go. I'm going to try and do table of values method and I know the function so well method all together at once so you can see both potential methods. So this thing has x values. It goes x less than 0, then between 0 and 3, and then greater than or equal to 3. So I know my table of values should go below 0 and should go above 3. I'll exaggerate it a little bit. So negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6. That should be enough to get all my features. So when completely confused, you just go through the table of values and find the individual points. I think you'll find it helpful to draw lines here when the rules are going to change. In there. So take the x values and sub them in. -3 plus 1 in the section for x less than or equal to 0, I get -2. -2 plus 1, I get -1. -1 plus 1, I get 0. And 0 plus 1, I get 1. Okay? So for table of values people, you just do that. For people who really know the function, and I say graph y equals x plus 1, and they go, y equals x plus 1. I've been graphing that since, grade 9. I know how to graph y equals x plus 1. So then you would take your line here, and I'm going to do it by hand so I can erase nicely, okay? So I don't know how good this will be on my screen. I'm not going to use the straight line tool. Y equals x plus 1 is just the straight line with y-intercept 1 and slope 1. There it is there. Ooh. Totally missed. That's why we use the other rule. So I'm going to switch to a straight line ruler here. Y equals x plus 1. Yeah. So you draw this whole thing. And this is kind of a mistake to do this. But I'm going to show you how to fix the mistake. So there's the line y equals x plus 1. So you go, oh, I know how to graph y equals x plus 1. And you draw the whole thing. And then you go, oh, that's only for x less than or equal to 0. Oops. Yeah. And then you go back and you say, okay, I got to get rid of this part of the line here. And so you get your erase road. And you erase that part. And all you're left with is this part of the line. And that's a totally legitimate way to handle this situation. Is just to graph the line and erase what you don't want. Yeah? Now this was x less than or equal to 0, so now I need that less than or equal to, I need that closed dot to let everybody know, yes, that point is included on the line. But not all the stuff over here. Then between 0 and 3, it says graph y equals 2x plus 1. You could build your table of values. You could just go, okay, I don't know what it's doing between 0 and 3. So I'm going to plug those in there. I'm going to change colors here on you. If I sub in 1, I get 2 times 1 is 2, plus 1 is 3. 2 times 2 is 4, plus 1 is 5. I just sub those in there, and I get 2 new points for my next section of the graph. 1, 3, and 2, 5. And so you could just then draw your line for that section in there. Other people are like, no, I know how to graph 2x plus 1. Yeah, you start at 1. I'll switch to straight lines. You start at 1, and you go up by 2s. And you draw this whole line. And you go there. That's y equals 2x plus 1. I don't need my table of values to do all that. But then you look and you go, oh, but I was supposed to stop at 3. So then you erase the part that goes past 3, right? So you go only out to x value 3 there, like that. Now what's weird about this one is, this is an open circle for that part, but it's a closed circle for that, so you won't really know the difference. It's continuous there. It might not be. They might not match up, and you might get discontinuous. And then there's open circle here, so we just do that open circle to let everybody know, look, look, it's not filled in. Open circle, yeah? I'm going to get out my white pencil and really show that's an open circle there. Can you see that better? Open circle. Okay. Then last section, 4 minus x squared. And this is where the table of values can really bail you out. Because even if you've graphed this line, and you're now like, now 4 minus x squared, am I really going to draw this parabola from here all the way down through here? Yeah, you could. And then erase the parts you don't need. Absolutely. But I think the table of values really helps here. I'm going to sub in 3. Let's see, that's 4 minus 9 is negative 5. Ooh, new color. Purple. I get negative 5. 4 minus 16 is negative 12. 4 minus 25 is negative 21. 4 minus 36, negative 32. I know none of those are going to fit on my graph. I get that. I'm just showing you how it's done. Did I sub those in right? 4 minus 9 is negative 5. Yeah, 4 minus 16 is negative 12. Well, you're going to punch these in your calculator. You haven't been doing stupid parabolas for 30 years like I have. 30 years? Scary stuff, right? 30 years. Is that possible? So you're going to just punch these in your calculator. You go 4 minus 3 squared, 4 minus 4 squared, 4 minus 5 squared. And then you get the points you need to. 3, negative 5. I'm going to make a mistake here, okay? Oh, no, it's not a mistake. It's a closed circle. Okay, 3, negative 5. There it is right there. 4, negative 12. Well, I can sort of put that one on there and then off the page. And that might boggle your mind, what's happening there, if you don't know your functions pretty well, to go, oh, this is a parabola, downward parabola. It's not weird at all that this thing is doing the old take off like crazy thing. Yeah, like a downward parabola, it would be like this. The rest of this parabola would like do 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 like that. You know, so. Okay. Oh, close circle. Desmos, big help here too. When you get stuck on one of these, like, why does this look like this? You graph 4 minus x squared on Desmos, and you go, oh, yeah, it's this whole thing here, and I'm only looking for that part there. Yeah, very helpful. Any questions on that example? Pretty nice stuff, as long as you're good at transformations and graphs, and all that stuff is taken care of. If all that isn't taken care of, well, this is going to be a complete disaster because you won't even know what you're doing and what you're graphing and so on.